Our next topic is comparators. We know the meaning of the word compare. Comparing means, we what we call we compare two people means we compare one person with the other. Similarly, in the case of logic design, when we hear the word comparator, what we do is we compare two different set of numbers. Okay, or we compare the magnitudes. A comparator is a logic circuit used to compare the magnitudes of two numbers. Okay, used to compare the magnitude of two numbers. Okay, when we hear the word comparators, the first thing that should be there in our mind is we are familiar with the gate XNOR. What is the specialty of XNOR gate? A, B, and what we call the output. Okay, in the case of XNOR gate, the output, if it's 0 0 0 1 1 0 and 1 1, A, or you can write this as A XNOR B, a dot and a round around it. Okay, 1 0 0 1. What's the specialty? Most probably we have learned, most frequently we can see the use of XOR gate. Okay, XOR gate means 0 0 the value will be 0, 0 1 value will be 1, 1 0 the value will be 1, and 1 1 the value will be 0. Okay, but XNOR is a gate, or it's a gate where the output becomes high when both the inputs are same. Okay, 0 0 means 1, 1 1 means 1. Okay, and XNOR gate is also called equality detector. Equality detector. Other name is coincidence gate. Coincidence gate. Okay, then about our problem. How can we say that two set numbers are equal? Okay, for that let me give you an example. We have two 4-digit numbers or 4-bit numbers. Okay, A3, A2, A1, A0 and B3, B2, B1, B0. How can we say that these two numbers are equal? We can say these two numbers are equal if A3 is equal to B3, A2 is equal to B2, A1 is equal to B1 and A0 is equal to B0. Right? For example, if you didn't understand this part, we can say that 1, 2, 4, 1, okay, is A3, A2, A1, A0, and B3, B2, B1, B0 is also 1, 2, 4, 1. But when we compare two numbers are equal or two marks are equal, when we have the same magnitude there, right? So, we compare A3 with B3, 1 with 1, 2 with 2, 4 with 4, 1 with 1. Again, we say that those two numbers are equal. In the case of equality detector, when we use the equality detector or the XNOR gate, here in this case the equality is written by or shown by A3 XNOR B3 and A2 XNOR B2 A1 XNOR B1 and A0 XNOR B0. Okay, let me check. Yes, this is how we represent equality here. Okay, then if someone asks you how can we represent the block diagram of a 1-bit magnitude comparator, just draw a box. We write here 1 bit magnitude comparator, 2 inputs A and B, and the output will be can be less than, that is when we compare A and B, A can be less than B, A can be equal to B, and A can be greater than B, right? Thus leg stands for less than, equal to, and L stands for less than, E stands for equal to, G stands for greater than. Okay, please go through. Okay. This is 1 bit magnitude comparator, the design. Okay, so first we write the logic is as follows. Okay, let the 1 bit numbers be A is equal to A0 and B is equal to B0. Okay, if A0 is equal to, okay, A0 is equal to 1 and B0 is equal to 0, A0 is equal to 1 and B0 is equal to 0, then what happens is A is greater than B, right? A is always A is greater than B in this case. Okay, A is greater than B. So we write an expression for G as G is equal to value of A0 is 1, B0 is 0. We write this as A0 into B0 bar. Okay, next condition is if A0 is equal to 0 and B0 is equal to 1, then A is less than B, right? A is less than B. So we write this as L is equal to the value of A0 is 0. So we write this as A0 bar B0. Third case is if A0 is equal to B0, A0 is equal to B0. I think it's yeah. That is if A0 and B0, I will write the condition in an elaborated manner. If A0 and B0 coincide, that is A0 is equal to B0 is equal to 0, or A0 is equal to B0 is equal to 1, then we write A is equal to B, which is equality, E is equal to A0 XNOR B0. Okay, 3 cases. And the next thing is about the construction. So before that we need to have the truth table. So we write the truth table, we draw the truth table as A, B and L, E, G. Okay, we have 0, 0, 0, 1, 1, 0 and 1, 1. Okay, when both A and B are zeros, we write this as equality. So equality becomes 1, the rest becomes 0. Same is the case here also. Equality becomes 1, other cases will be 0. When A is less than B, we have the condition less than. When A is greater than B, we have the condition greater than. We check. Yes, 1, 0, 1. Yeah, it's correct. And the design part, actually we have XNOR operations, and also less than condition is there, greater than condition is there. So what we need to do is draw A0 and B0, right? Let me check. Yes, A0 and B0. First, go for the equality case. Okay, E is equal to A XNOR, A0 XNOR B0. In the case of less than, we have a bar here. So what we do is, next is, in the case of greater than, we have A0 A0 B0 bar. Let me check it. A0 B0 and yes, okay, 3 cases. Okay, if you want, we can also write here A less than B, that is less, A equal to B is equal to, or A greater than B, that is this. If you want, okay. Any manner you can write. Either you can write these expressions like this, or you can go for these cases. Okay, follow just one. Clear?